So let's take a look at this problem. We want to find a vector equation for the intersection of two planes. And pretty much the picture that we should have in mind is something like this. So you have your two planes, and this is their intersection. It's a straight line, it extends indefinitely, and you would like to find a vector equation for it. And let's recall that in order to find the vector equation for a line, we need a point on the line and a tangent vector. I'm sorry, a parallel vector, not a tangent vector. So if the vector is, let's say, ABC, and you have the point x naught, y naught, z naught, then the equation of the line, or a vector equation for this line, is r of t is equal to x naught plus ta, y naught plus tb, and z naught plus tc. The way I like to think about this is that you vectorize the point, so you make a vector out of the point, and you add t times the direction vector. That's an easy way to remember how you find this equation. Of course, there's an alternative nice way of finding the equation of a line, and that's when you know 2 points that belong to this line. So if you know that the point x naught, y naught, z naught, and x1, y1, z1 belong to this line, then a vector equation for this line is simply 1 minus t times the vectorization of the point of the first point plus t times the vectorization of the second point. Now, it's funny that I mentioned these two ways because one can solve the problem in both ways. However, I would like to really focus on this. So I would like to find a point that belongs to both planes. And then I would like to find a vector which is parallel to the line of intersection. So, of course, here's the funny thing about it. If I say that I'm going to find one point that belongs to both planes, one might say, well, okay, so why don't you find two? And then you have your equation right there. And that's absolutely right. One can do it this way. However, I think that there's something remarkable to see about the first approach. So let me begin by finding a point that belongs to both planes. So how do we do this? I mean, we really have to solve this system. So we have to find x, y, z that satisfy both of these equations. And these are two equations, and they have 3 unknowns, which means that we have more flexibility that one could ask for, and potentially we can find infinitely many points. Not potentially, we know that we're going to find infinitely many points because those points form a line along which the two planes intersect. And of course, by the way, one could ask, how do you know that these planes intersect? I mean, what is it that makes you sure about that? It's the fact that these two planes, if you look at normal vectors for these planes, so this plane has normal vector 1, 2, 1. How did I find this? I look at the coefficients of x, y, and z, and this has a normal vector, meaning perpendicular vector, 1, 1, negative 1. Since these two vectors are not parallel, and you can tell that they're not parallel because one is not a scalar multiple of the other, then the two planes cannot be parallel either. So they're going to intersect, and we want to find this intersection. Actually, in a moment, you will see that I will want to use these two vectors, so I'm glad I wrote them down. But for the moment being, let's focus again on finding a point. So how do you find a point that belongs to both planes? How do you get around the fact that you have two equations with 3 unknowns rather than 2 equations with 2 unknowns? The answer is very simple. You want to work with two equations with two unknowns. And you can do that by just arbitrarily setting one of the three unknowns to be a specific number. And it is possible that you do that and the system of two equations and two unknowns that you get does not have a solution. That is very possible. But here we can easily set z equals 0. By the way, if what I said before just happened, then you would just proceed with a different unknown. You can always set an unknown to be a specific value and get a system that has a solution. So if we set z equal to 0, then we're going to get x plus 2y is equal to 1, and x plus y is equal to 3. Actually, now that I wrote it, I think setting y equals 0 would have been even more convenient. Anyhow, let's not worry about that. Again, like I said, it can be done in infinitely many ways. You can give this task to 10 people and they will come up with 10 different points. But in any case, how do we solve the system? Just subtract the second equation from the first, and that will give you y is equal to -2. Once you know that y is equal to -2, easiest thing is to plug it into the first equation and get x equals 5. So if you put everything together, you have that the point 5, -2, and 0 belongs to both planes. Okay, so this is something that we want to use. So let's keep it in a nice frame so that we remember it. And then let's try to find a vector which is parallel to this line. And this is where things get really nice, because think about it. I think the best way to visualize it is to get a book, open it somewhere in the middle so that the angle between the two pages is, I don't know, some acute angle, and then try to visualize the normal vectors. Do you see what is a direction which is perpendicular to both vectors? Yeah, you guessed it right. It's going to be exactly the direction along which the two pages connect. So in other words, the intersection of the two planes is precisely perpendicular to the plane formed by the two normal vectors. So in other words, if I want to find the vector which is parallel to the intersection, all I need to do is take the cross product of the two normal vectors. And that's precisely what I'm going to do. So I'm going to have 1, 2, 1, cross, 1, 1, -1. Let's see if we remember how to take the cross product. So I, J, K, 1, 2, 1, 1, 1, -1. Delete first row, delete first column. You're left with a determinant 2, 1, 1, -1 on the lower right corner. That will give you -2 minus 1, that's -3. Delete first row, second column. You're left with a determinant 1, 1, 1, -1. That gives you -1 minus 1, that's -2. But it's the middle coordinate. Always remember that extra negative sign that the middle coordinate takes. That makes it a 2. Finally, delete the first row and the third column, and that will give you 1 minus 2, that's -1. Here's your normal vector. I'm sorry, the parallel vector to the line. Here it is. So I claim that by putting these two things together, we can easily find the answer. And what is the answer? So we're going to have that R of t is, we wanted to go through the point 5, -2, 0. So we vectorize this point. And we add plus t times -3 to -1. Okay, so here's a vector equation for for the line of intersection of these two planes. Please note that everything that I did here on the right was just some theoretical reminders. What you need to really write is what you have here on the left. Study this problem very well because it gives you very good amounts of information for both plane and line equations. Thanks for watching this video.